Okay, so just review of things that we have done. So we're looking at estimating distribution of alphabet of size k, and we're asking how well can you estimate those distributions with n samples. Okay. And on the first day, we started by looking at what happens when you make no assumptions. So you just want to estimate the distribution, you don't know anything, and then you said you can look at the empirical frequency estimator, and in terms of L1, it will achieve roughly square root of k over n. That's going to be your distance. And we said, and this is also the best you can do. And we said that that's not very good because it just goes like 1 over square root of n. So the number of samples you need is quadratic, which goes very large, very fast. Okay, so then on the second day, we said, okay, what can we do to avoid this growth? And we said one thing that people do is assume some structure on the distribution. And for example, we gave the example of a monotone and envelope classes. So for example, for monotone, you'll see that it will, instead of k, you already start going from log k, so it's a lot faster. Okay, and then yesterday, we said, what if you don't want to make assumptions of the distribution? You don't want to assume that it's monotone, for example. And then we said what you could do is maybe you could change your criterion a little bit. Instead of estimating exactly the distribution, just estimate the probability of things that appear at any given number of time, which is in some sense anyway the best you can do because you cannot distinguish between them. And we said that once you do that, then we said you could look at good Turing and some modification of good Turing, and then you get a new estimator, and it approximates this combined probabilities at a rate of 1 over n to the 1/4. So now k disappears completely from the picture. Okay, so there's no dependency on k, so it applies to all alphabets, any distribution, and even infinite alphabets. Okay. And what we want to do today is we want to talk about some applications, and they'll include things like classification and other things, and properties of distributions, and maybe a little bit talk about continuous distributions. And the approach that we'll take is that of competitive. So we're trying to do something that is essentially as good as what anyone can do. Okay, so that's our approach today. All right. Okay. So the first application we'll talk about is classification. So I'll start with a simple example. So you have two unknown discrete distributions P and Q, alphabet size k. They're unknown, and you get some training samples. From P you get some sequence X of length n, and from Q you get another sequence Y of length n, drawn IID according to P and Q. And then you get some Z, which is drawn either according to P or according to Q. You don't know which. And for simplicity, we assume that they're equally likely. Someone flips a coin, takes either P or Q, and selects an example from P or from Q according to the distribution. Okay. All right. And the question is whether Z was generated by P or by Q. Okay. And so let's do a few examples here. So suppose we take 3 samples. So P will generate x1 up to x3. Q will generate a sequence Y of length 3, and then we'll get Z. Okay. So for example, suppose that the P generated the sequence AAB, and Q generated the sequence BCB, and now we get A. So most likely we'll say that Z was generated according to P or according to Q. Obviously, according to P. Thank you. So because it's closer to the X sequence, so generated according to P. Now suppose we see B as Z, what would we say? Most people would say, obviously, Q, and they'll be correct. And if we get C again, it's reasonable to assume that's generated similar to Y. It's generated according to Q. And let's say we get D, then maybe we don't know. Okay, so we don't. This is what we're doing. I think it's very clear. So what are applications of this problem? So for example, spam filtering, you get a lot of samples of spam mail and a lot of samples of legitimate mail. And then the new mail comes in, you want to say, is it legitimate or is it spam? Or your Netflix, you see a lot of movies that someone liked and a lot of movies that that person did not like, and you want to decide whether you want to recommend to them some movies. So you try to see if this new movie is more like what I liked or didn't. Medical diagnosis, sick people, healthy people, a new person comes, or different diseases if you want. A new person comes with certain symptoms you want to classify. Stock recommendations, good stocks, bad stocks, and so on. A lot of different things, and you could argue, yes?
So I'm just thinking about the examples you gave, right? For the first two, isn't everything going to come out like D?
What do you mean D?
In your example there? Like for spam filtering or movie selection, isn't every case you say, you have some movies the person likes, some movies the person doesn't like, here comes a new movie.
Right.
It's going to be a new movie.
No, so I'm sorry. So maybe this is not like, it doesn't follow exactly this thing, but the assumption is that there's a distribution. There are movies made by, of course, if you knew that ahead of time, you wouldn't, but there are movies in a romantic style. They all have the same distribution. There are movies in some other style, like action film. Okay, they're made by a different distribution, and now you get a new movie, maybe it's not classified, and this person, you don't know, but so it turns out that this person likes that and doesn't like that. A new movie comes out, you look at some features, and based on that you want to classify. Does that make sense?
And you expect the feature bundle to be exactly like a feature bundle you've seen before?
Okay, so what we expect is this. So we expect that there's a distribution. So if you want, you can think that you have decided ahead of time on some features. The features, the length of the movies, the names of the actors, and so on. So you have some feature space, okay? And there's some distribution. For the good movies will have some distribution over the space. The bad movies will have another distribution over the space. Now, we don't know these distributions ahead of time. So if you want, you can say, I learned them from these. But maybe we have a different way of doing it. Doesn't matter. But one way is to learn the distribution and learn this distribution. And then once you know the two distributions, we'll talk about it. What happens if you know the two distributions? Maybe you can make a good decision.
What I'm asking is, it seems to be that those examples both have some kind of topology.
Oh, that's right. Okay, very good. Okay. So we'll talk. Very good. Okay, I apologize. Yeah, absolutely. So this is over discrete sets. So we have a distribution of discrete sets. One of the things we'll talk about is when you have topology. You'll see. We'll talk a little bit about that as well. But you're totally right. Okay. So basically, you can argue that everything in life is based on the past experience, right? And so, right. Okay. So. So first, let's talk about the omniscient classifier. That's not a scientist that drives a Dodge Omni. It's a classifier that knows everything. Let's see what that classifier will do. So this is a classifier that knows P and Q in advance, knows the distribution of good movies, knows the distribution of bad movies. Okay. So in that case, the classifier's problem just becomes hypothesis testing. They know the distribution P, they know the distribution Q. Z comes in, they need to decide if it was generated according to P or according to Q. Just classical hypothesis question. Hypothesis testing problem. So what they can do in this case, they don't need to look at the training data because they know the distribution. It doesn't help them. Okay? And they just classify Z to the distribution that assigns it to the higher probability. So if P of Z is, let's see if I wrote this down, yeah. If P of Z is bigger than Q of Z, then we'll associate it with P. And if P of Z is less than Q of Z, we'll associate it with Q. Is everyone 100% okay with this? Okay. Right. So if you knew the two distributions, you always, and you assume they're equally likely, the two hypotheses, then you look which one assigns more probability to what you observe, and that's what you should do. Okay. Okay, so that is kind of clear. Okay, but of course, this omniscient classifier requires knowing P and Q in advance. So you need to know the distribution P and distribution Q in advance. In reality, that's never the case. Like if we look at movies, you don't know what is the distribution of good movies, the distribution of bad movies, sort of the thing you want to learn.
This is maximum likelihood, right? This is maximum likelihood.
No, okay, so you're talking about up to here? Just a second. You're talking about at this point?
It's maximum likelihood.
Yeah. It is maximum likelihood, not in the sense that we've you're looking for the distribution that gives it the higher probability, and that's the one you select. So if that's what you.
Yeah.
Okay.
Yes, that's what I'm saying.
Okay.
That's what you were saying too.
No, because there's a different maximum likelihood here that may not work, which is how you because you. I'm sorry, that's what I was asking, because you're asking about here. And you need to learn the distribution, and then you can learn the distribution is maximum likelihood, so I wasn't sure.
Okay. That's okay.
Yeah. All right. so this requires knowing P and Q in advance, and so for any pair P and Q, you'll need to use a different classifier, right? Which you can't because you use a single classifier. Right? So it's impossible. Okay. All right. So let E star of P and Q be the error of the omniscient classifier for P and Q. So for every two distribution P and Q, there'll be their omniscient classifier that's designed based on these two distributions. It's written here. And it achieves an error, which is E star. This E star, the error is, in this case, is simple. You look at all possible values Z. You look at the lowest probability. You sum them up and divide by 2. That's the error of this classifier. But that's not so important. Whatever it is, it is. All right. And as we said, achieving E star requires knowing PQ in advance, so it's impossible. So the question, of course, is whether a realistic classifier, one that does not know P and Q in advance, can approach this E star. Okay. So that leads us to the definition of competitive classification. So what we want is a classifier that performs nearly as well as the omniscient classifier. And remember, E star of PQ is the lowest error of any classifier for P and Q. It's our definition. It requires knowing P and Q in advance, therefore impossible. And if you have another classifier C, so you come up with any classifier, call it C, then it will, for P and Q, it will make some other error, which is EN P and Q, which depends on the number of samples that you have seen. E star does not depend on the number of training samples because you don't need to even look at them. So you can think of infinity. And now, given some number of samples N, and you come up with a classifier, then this is the error of this classifier. Okay? Right. And you can define the degradation of the classifier with n sample to be the largest error increase. So it's the maximum of all distribution pairs P and Q of the error of this classifier minus the best error that you can do for these two distributions. Is that clear? So come up with a classifier, call it C. Maybe for some P and Q it will be optimal, but for others it won't be optimal. So you look at this difference of your error minus the best error, and you look at the worst distribution, possible pairs of this pair of distribution.
This E is taking expectation over all the training that you can see?
Correct. It's over, this is over all the training and the test.
The test.
Okay. Okay. And so this is for the classifier C, and of course we're doing min-max, so we'll find the classifier with the lowest degradation possible, and that will be just a function of n. It's the minimum of all classifiers of their degradation. Clear? Okay. So this is the lowest guaranteeable increase in the error with n samples. So if you give me n samples, I can guarantee that my error will be my additional error will be at most something. Okay. And observe that the worst possible increase is 1/2. It will never be more than 1/2 because you can always take a classifier that randomly associates Z with something. So its error is 1/2. The E star is always at least 0. So the difference is at most 1/2. So this number dn is at most 1/2. Okay. And the question is whether you can get dn to be less than 1/2. For example, can you get dn to be 0.49. Can you build a classifier that you guarantee that with n samples, so let's say n is 1,000,000, can you build a classifier that when you give me 1,000,000 samples from X, 1,000,000 sample from P, 1,000,000 samples for Q, and then classifier, your error is going to be at most 0.49, at most that larger than the best possible. Yes.
Aren't these probabilities exponentially decreasing?
If you fix the P and Q, they decrease, and they might decrease exponentially. But we're looking, you're fixing n, because we don't want to see everything we're doing is not in what happens in in the limit. You fix n, like n is like 1,000,000, maybe even a larger number, maybe 1,000,000, and we want to be able to guarantee that your increase is not high. So it's not a question of exponential because.
Don't we have the Sano theorem, etc.
No, because okay, let me show you the next example.
For the omniscient.
I understand, yeah, but the thing is, we're not looking in the regime that we let n go to infinity. We're not doing things for n going to infinity, looking at the behavior. We're looking at n, which is a fixed number. It could be 1,000,000,000,000, I don't care, but it's a fixed number.
Why do you use the word always? I don't understand the word always.
Because we're looking at the maximum of all of all pairs of distribution P and Q. You can come up with a classifier that will be very good for two specific distributions, but will be bad for two other distributions. And the issue is that you don't know ahead of time what the distributions are. So you want a classifier that will work for every P and for every Q.
You also don't have a bound on the alphabets of P.
Correct. That's correct.
You can make it much
Correct. Correct. And we'll see that in the next example. And that's why the exponential regime will not kick in at that point.
Then obviously no, right?
Because?
Because if you can let K to be arbitrarily large, then you can probably present some training which has no information at all to the classifier.
Right. Okay. Very good. Okay. So
You are fixing n, but letting k be arbitrarily large.
correct.
Okay.
Okay. So the first thing to see is that actually you cannot do better than half. The best you can do guarantees a half. So given any n could be arbitrarily large, let k be 4n, so we're making k even larger. Okay, and mind you, this is a reasonable thing. Like we said, the size of English is, 500,000, and you need to look at given the context and so on, and let P and Q be uniform over disjoint subsets of 1 up to k. So this k is the alphabet, and you take half of it, and P is disjoint over one half, Q is disjoint over another half. For example, P is disjoint over the first half, and Q over the second half. Or P is disjoint over or P is uniform, over the evens, and Q is uniform over the odds. Okay, so there's disjoint, P and Q are disjoint and uniform. Okay, so here's, for example, where n is 5, so we took k to be 20, and then we get P and Q to be uniform over half of the elements, 10 elements, disjoint. Okay, so what is E star in this case? 0. Everyone agrees, right? Because they're disjoint. So if we know P and Q, and we see a sample, if it comes, so we know that P is blue and Q is red. So if the sample, if Z is blue, we say it's P. If B is red, we say it's Q. And this works for any n because we know P and Q. We don't need to learn them, so it doesn't matter what n is. So E star is 0. On the other hand, what is EC? If you come up with any estimator, what is the best error that you can guarantee? So notice that n is chosen to be k over 4. Okay, so that implies that the number of samples that you'll see every time n is the number of training sample. Any training sample consists of a sample from P and a sample from Q. So at most you get 2 samples. So you'll see at most k over 2. You'll see at most k over 2 samples. Okay. Now the probability that Z will not be one of those k over 2 samples is at least 1/2. So for example, here we take 5 samples. So maybe this is the first sample. We saw 2, 4, 6, 8, 10. We saw 10 samples out of the alphabet of size 20. The probability that Z will not belong to any of them is 1/2. So it's at least 1/2, and therefore the error that we'll commit is at least 1/4, because at that point we need to guess. So that implies that the error is at least 1/4 for any classifier. Okay, and so therefore the best that we can guarantee is at least 1/4. And if we take k to be much larger than n, then we can get 1/2, right? So if we took k to be like 1 billion times n, then you get as close to 1/2 as you want. Is okay? Right. Okay. So what that tells us is that if we look at the best degradation that we can guarantee, it's actually 1/2. We cannot guarantee doing anything better than 1/2. Yes.
So we're looking at additive degradation, and this E star can be 0 or 1, depending on P equal to Q or on the disjoint.
Okay.
So, for example, is it a problem with this additive thing? For example, you use with a factor of
ratio.
Well, like in this case, no, because I think not, because in this case the E star is 0. So if you try to do it multiplicatively, it's even worse.
Infinity.
Even worse. Okay. So this falls a little bit in what we discussed yesterday, which was the art of the doable. How can we modify the problem so to make it possible? Okay. And our goal is to modify the problem, 1, in a way that will make it possible, 2, in a way that will show that what Good and Turing did, like looking at the combined estimation, is actually useful. What we discussed yesterday, that we didn't just arbitrarily decide to combine. It's actually useful. And 3, maybe get some results that are nice. Okay, so let's talk about that. So let's talk about label invariant classification. So E star, the omniscient classifier, requires knowing P and Q in advance. Okay, and that's maybe a little too much power to give the estimator. Like to compare ourselves to someone who knows the distribution in advance. Nobody knows that. So that's a little too much power maybe to give this classifier that we're comparing ourselves to. So no real classifier knows that much. So maybe we can make a natural modification and compare to more realistic classifiers. And these classifiers are called label invariant or canonical, also called classifiers. So to see what they are, let's look at an example. So again, three training samples for X and Y and then Z. So suppose the training samples are A and B and CBA, and the test is A. We'll classify it someplace, okay, wherever it is. Okay. Now let's look at a new sample. So now we have UUV and WVU, and the test is U. Okay. If we have a reasonable classifier, what can we say about the two classifications? This, how we'll classify this one and how we'll classify this one. Can we say something about that? Must be the same, because we just rename things. This is a classifier in English, AAB, and this is a classifier that A is U is in French maybe, A is U and B is V and C is W and so on. So there's just a relabeling, right? There's like a one-to-one mapping from both the X, the Y, and the Z, all of them, the same mapping that A goes to U in all of them, and B goes to V in all of them, and so on. So in that case, it's clear that this classifier should give the same answer as this classifier. It shouldn't be that someone who does classification in Greece will do something different than someone who does classification in, I don't know, in China. Okay, it has to be the same. Okay. So what's that?
And that's, you know the meaning of the language, right? Or the words?
No, I don't think so, because we are learning from scratch. So if you know more, you should incorporate someplace. But here you're just giving samples from the distribution, trying to learn. Like you're giving emails, you have an algorithm, you wrote it in, it works for English, it works for French. Okay. So in both cases, classification should be the same. So in other words, if you have consistent relabeling of all of them, if you had for just one of them, two of them, that would not apply. But if you have consistent relabeling of all of them, then we should have the same classification. And as we said, they're called label invariant or canonical classifiers. Canonical because that's the all reasonable classifiers are like that. So if you assume no prior knowledge, like David was going to assume prior knowledge, if you assume no prior knowledge, then all natural classifiers are canonical. So what we can do is we can just do the same thing, and we can define E star tilde. The tilde will stand for classifiers that have to be label invariant. Okay. And notice that achieving this E star or E star tilde also requires prior knowledge of P and Q. You cannot achieve this. You cannot achieve this performance without knowing P and Q in advance. Okay, and we let dn tilde to be the degradation of the best label invariant classifier compared to the the best compared to the omniscient label invariant classifier. So again, we compare label invariant to label invariant.
Is it obvious how to compute this?
No, not easy, not obvious at all. You should be looking at essentially the patterns we discussed yesterday. But do for both of them. So you look at these symbols, how many symbols appeared 3 times here and 4 times here and appeared here and so on.
So there's a polynomial time algorithm?
No.
No? Okay.
No, because you need to look at all possible permutations.
Oh, I see. Okay.
So you see why, right? You need to look at all possible permutations of the symbols that could give you that.
Okay.
Wait, I have a...
Yes.
What does it mean, omniscient label invariant?
So a label, an omniscient, a classifier can be invariant and can be variant, right? It could look at the values and say if the value is like the word, Berkeley, it will do something else. That's label variant. It takes into account what the values are. A label invariant is such that if you permute these things, if you relabel them, it'll give you the same answer. Okay. Now you can try to minimize the error, over all classifiers. So that's what we did in the previous slide. You can minimize this error over only classifiers that are labeled invariant.
Just can you explain why that one that minimizes the values of the two is not labeled invariant, just to get some intuition?
Oh, no, typically, or why it's not labeled? Okay, perfect, okay. Let's look at the example that we had before, this example. So if you know the two distributions, then you know P and Q, namely you know that this is P, this is P, this is P, this is P in this case, and you know which is Q. You know that Q was the red one, you know that these are Q, okay? So now when someone gives you Z, okay, then you look at see whether Z is here or here or here, and then you decide, okay? This is clearly labeled invariant because here in this example, I only gave you 5 samples. Okay, I gave you n was 5, so you got 5 times 2, 10 samples. And suppose this was the value. Okay, the best labeled variant classifier will classify this into P because it sees that. Okay, but now suppose we relabel this one to this one, so we're not relabeling any of the training. We're just relabeling the test, which did not appear. So it should be classifying into the same one. Because suppose your training was A, and the other one's B, 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 something, or B, B, C, let's say, and D, something you've not appeared. Let's say this classifies it into this one. Okay? Now I'll change this to something that is completely different here. We've not seen it before. If it's labeled invariant, it should also classify it into this one.
This is a pathological example where you're forcing it to be classified the same way for something that has not been seen, right? I mean,
no, I wouldn't. I don't think so because I agree that this example is not maybe super common, but it's easier for us to describe. This is not what will make things possible and not possible. But I just want to show you why the label. Yeah, you could make things that things appear a few times, and with this I can explain to you why it will not work. If I had made it more complicated, then you should trust me that it still won't work, but it will be more difficult to show you because you need to do some calculations. But you agree that this one, if you want to achieve 0 error, then it has to be labeled variant. Is that okay? Yes.
So in the label invariant case, you're considering only deterministic classifiers?
That we're considering that, but you can show that the best classifier will be deterministic.
But again, so in this case, for example, if you do random, if you choose P and Q randomly for D, which has not appeared, then the worst case it does better than deterministic, right?
The worst case does better than
Okay, so you're saying that even if you make a deterministic thing, it's
right.
As good as random.
Correct. Okay, but yeah, we will consider deterministic, but I don't think there's any reason for you to look at randomized. Right, because you're choosing, if you have a randomized one, you're averaging over a bunch of deterministic ones, and just look at the one that gives you the highest one. Right. Okay. Any other questions? So it's clear? Yeah.
To mean that like your classifier just gets the number of times that he doesn't get each letter, he gets just number of letters which gets one time number with.
That's correct. So another way, one way to say it is that the way I said it, that is that you want a classifier that if you relabel, the classification stays the same. An equivalent way of saying it is what he was saying, that you want a classifier that just you look at, you say how many letters appeared once here, and then twice here, and 3 times here, and you just keep those counts, and based on those counts, you make your classification. It's more like the profile that we had yesterday, but 2-dimensional, or 3-dimensional if you include. Right. Okay. So also requires knowledge of P and Q, and we said what is dn, and dn tilde. So we know that dn was half, and the question is whether dn tilde can be smaller. Okay. All right. And the reason to do it is at least if you're designing your classifier based on the worst case, then here, 1/2, you know it's 1/2. It doesn't give you anything. So you need to come up with a different measure that you say my classifier is good because it works, well in all cases. Okay. So first, let's show. So again, we're trying to look at what dn tilde is. So let's look at the empirical frequency classifier first. So for example, if you have A, B, C, B, A, and A, we'll classify. So we'll look at the probability that A gets here. It's 2/3. Here it's 1/3. So we're going to say it goes to P. And here we have C. So C appeared once here and twice there. So we'll say it belongs to Q. Okay. And the question is, so what is the optimal classifier? So one possible thought is the empirical frequency classifier, we call it F, that assigns the training, which assigns to the one, we're training the distribution based on these training sequences, and we assign the test to the one with the highest probability, namely we assign to the training with where Z appeared more times, then it kind of takes the distribution that assigns to Z the higher probability, which is what we said we need to do. We need to assign, this is what David calls maximum likelihood. We need to assign Z to the distribution that gives it the higher probability. Okay, and you notice that this is label invariant. This estimator is label invariant. If I'm going to change A, B, A and B to alpha and beta and so on, it will still assign the same. So this empirical frequency is label invariant. So it kind of should be, or is it clear that it's optimal?
So optimal means in terms of the comparative difference.
Correct.
Compared to the label invariant.
Invariant, correct. So what do people think?
Clearly optimal.
So we're here, we're still in the world where K could be much larger.
Correct. K could be anything.
But then it could be that so clearly optimal could be equally bad as something trivial.
That is true. If indeed dn was 1/2, but maybe in this case it's not 1/2.
Okay, but you would still call it.
Yeah, I mean that's okay. It's one of many optimal. That's okay.
So I'm just curious about something. So you mentioned these two senses of label invariant, but one of them is allowed to take into account when something appears.
The location does not matter because it's IID. So actually,
if you're comparing against the best one, if you're allowed to look, you can cheat. You can see that, for this particular condition.
So just 1 second. When you say where it appeared, I just want to make sure I understand. Do you mean that A appeared before C, or yeah? That we're assuming that the samples are IID. So one could say that there could be another level of label invariant or canonical, that you should say that if you permute those, if you permute the sequences, it should also give you the same answer. That will not make any difference. Because it's IID, so you should not have, you don't gain any information from the fact that you saw CCBA or if they were like this. So if you want, you can add that level of abstraction and it will not make a difference.
Clearly optimal. Is there a question mark or no question?
That's my question to you, I guess. So, okay. So why, right? I mean, okay. So we don't see that it's optimal, right? It looks like it could be, but maybe not. So what we'll actually show is that it's not competitive with label invariant classifiers. It's actually not optimal.
What does that mean? Sorry.
So what that means is that if your classifier, your classifier in this case is this. You get a letter, you look at the test, and you try to classify it. Look at the sequence where look at X and look at Y. See where Z, this C appeared more times, and classify it there. If that's what you do, you're not achieving this. Your D star tilde, or your error, your degradation is not optimal.
Just to clarify, when there's a tie, what do you do if you have not seen it?
Then so if you use the empirical frequency, maybe you just randomly.
It's not about ties. It's not that you will come up with another one.
No, that's not about ties. It's not about ties. No, it's not about ties.
Not competitive means that you're not minimizing that gap.
Correct.
It's not like you can achieve that D tilde, right?
So maybe we'll see. Maybe achieve. The question is what is D tilde? What is D tilde, right? So D tilde is some number.
There may be no scheme that can achieve D tilde. Is that right?
So our definition of D tilde is the one that's achieved by the best scheme. So our hope is that this D tilde goes to, of n, it's a function of n, goes down to 0. So we know that dn without tilde is 1/2, and our hope is that dn, this thing, goes down to 0 as a function of n. Okay, and so if you're looking, so what we're going to show now.
When you say comparative, you mean it goes to 0. Is that what comparative means?
Let's say, yeah. Mm-hmm. Yeah, that's a good.
And you're saying this does not go to 0?
Correct.
But it's not clear whether there is anything else.
Yeah, that's right. So we need a little patience for that.
I don't know.
Right.
In case of dn, if you bound k like to be much smaller than n.
But you could. That's not our interest. In this whole, all 3 hours, what we said was that.
One thing I know.
Yeah, that's right. What people have done in the past, we started 3 days ago, looked at small k and let n go to infinity. Then you get like exponential decay and so on. That's all great. But what we're saying is that if you want to do natural language processing, you're trying to estimate a distribution over English words, 500,000, in a given context, the previous 2 words. The number of such contexts is, let's say, 500,000 square. The number of samples even Google has with that many contexts is very small compared to 500,000. So we're not in the regime that your alphabet, that your sample size is much bigger than k.
High-dimensional statistics is another way of saying.
Sure. Yeah. Okay. So we'll actually, everything we do is see what happens when your alphabet is large. That's all. That's what we're looking at. Okay. So so what we want to show is that this is not competitive with label invariant classifier, which will make it clear. Sorry.
So even if it's competitive, the performance can still suck, right?
That's right. So it could be. So it depends. So this is not completely well defined. Let's define the next slide. You see. So it's true. It could be that the dn goes to like maybe 1/4 or maybe goes to 1/2, and the empirical frequency actually go to more than that. Okay. But what we'll eventually show is, or at least say, is that the best you can do goes to 0. And what we're going to show now is that empirical frequency does not go to 0. That's what we want to show now.
You get here only one sample of z or many?
In this particular case, we get a single sample of z. If you wait like 15 minutes, you'll see about more.
If you get one sample, it should be optimal.
It's not optimal.
Even if you get only one sample of z?
It's not optimal. Right. Next slide.
By the way, when you said you have to wait 15 minutes and you see, Erdo immediately look at the watch.
David, what's that? Yeah. We did. Yeah, we did really well yesterday when you were not around. There was no time limit. Everything was great. Okay. All right. Okay. So what we want to see is a lower bound on the error of empirical frequency classifier. We want to show that if you have a single test, it's not optimal. Okay? So what we'll show is that if you look at empirical frequency, F stands for that, then the degradation compared to other label invariant classifiers is at least 1.5%. Maybe not that much, but not optimal. Okay, and this is using a simple example. So let P be uniformly distributed on n elements, and Q uniformly distributed over the first two n integers. Okay. So what is the optimal classifier? We know that if P of z is bigger than QZ, then we need to send z to P, and otherwise to Q. Okay, if you know the probabilities. Okay. And in this case, it remains for this even though we'll be looking at things that there's a slightly different calculation that you need to do, but it remains the same. So now remember that x is distributed according to P and y according to Q. So let nz, so z is the test of xn, be the number of times z appears in xn. Okay. So if nz of xn is bigger than or equal to 1, namely if z appeared in xn, appeared at least 1. So if z appeared in xn, then what is P of z? If z appeared in xn, what is P of z? Remember, x, right, so P generates x, so P generates x, Q generates y, and now someone tells you that z appeared in x, so that means that z is one of those first n elements, and so P of z is 1 over n. Okay? If z if z appeared in yn more than once, namely z appeared in y, okay, that means that q is 1 over 2n. Therefore, if you have an element that appeared in both of them, appeared in x at least once and appeared in y more than once, then you should associate with p, which makes more sense because p gives a higher probability. Okay? And you also notice that this classifier is labeled invariant, right? Because if you rename things, it's the same. And so you classify as if it appears. Your classifier says if it appeared in both of them, this is p, this is q, you'll associate with p. But let's look at the distribution of nz of xn, the number of times that z appears in xn, right? So, we want to evaluate the performance of the empirical frequency estimator. So we see how many times it will appear here in xn, how many times it will appear in yn, and that's going to be our classification rule. Okay. So how many times will z appear in xn? Z it is distributed binomial of n and 1 over n, right? Because z is some number that is generated randomly, okay? And the probability that it will appear, so z that will appear in, so x is length n, and the probability that will appear in any of them is 1 over n, okay? And so it's Poisson 1. Okay. Let's look at the distribution of z in yn, okay? It's binomial n and 1 over 2n, right? Because it's, you have 2n values, okay? And so each probability is 1 over 2n, and you have to take n samples. Okay, so this is Poisson 1/2. Okay? But there's some probability that this number, even though it's Poisson 1/2 and this is Poisson 1, there's some probability that this nz will be bigger than 1, okay? And number of times that this will be reversed, namely that it will appear in xn, even though it's Poisson 1, fewer times than yn, and both of them will be bigger than 1. So there's some probability that this happens. When this happens, you'll be assigning it to the wrong one. You'll be assigning it to 1, whereas you should have been assigning it to x. Okay? So in this case, you classify to y instead of x, which is what you should have done. And so additional error is this probability, and then times 1/2.
But it's not clear if you see a small, so the maximum likelihood thing classifies all small numbers in the first, right? Okay. And the second one says, well, if you see a small number, you're not 100% sure it came from the first.
I'm sorry, so what?
But it's,
in order to be, I'm not sure if that's what you're saying, but in order to be optimal, what you need to do is for every value of z, every combination, you need to make the best decision because your error is the combination. So what we're saying is that in these cases, you did not make the best decision. In all other cases, I don't care what you have done. It's going to be the summation of these probabilities. But here, just on these, you're making at least this error.
Yeah. But it's not an absurd decision. It's not an absurd decision. It's just not the best decision. Yeah.
Okay, so that we're going to see. Okay.
Yeah. So the question is whether there's a better one, right?
Okay, that's right. So the question is whether there's a better one. Okay, so that shows that for empirical frequency, the additional error over the best labeled invariant classifier is at least 1.5%. So that's what I meant when I wrote vaguely that it's not competitive. So now we understand. Okay. So the question is whether it's something that is competitive. Okay. All right. Okay. So indeed, there is. So again, so recall the dn with label non-invariant. The best you could do is 1/2 away. And the question is whether for label invariant classifier, you can do better than 1/2. And what you can do is you can relate this classification to estimation of a sequence pairs, because you observe a sequence of x and y's. And you remember that we had, for what we described last time, you had an estimator that when you looked at the combined probabilities, achieved the best that you can, the error went down to 0, okay? And if you look at this second interpretation, in fact, so what you have here is you need to look at, you're not trying to estimate a distribution over values, but distributions over kind of profiles. Like so many symbols appeared 3 times here, and twice in Y, and then here appeared, and so on. And you try to estimate those probabilities. And we saw last time that for single sequences, you can do it, and you can modify the estimator to sequence pairs. Okay? I'm not showing this. And using that, you can actually build a label invariant classifier, which here it goes like at most 1 over n to the 1 over 5. So this does not depend on k. It doesn't matter what k is, what the alphabet size is, you can achieve it. So you can build a classifier. So we know that if you try to compare someone who knew the exact distribution, that's impossible. That you gave that person too much power. But if you just try to compare yourself to someone who knew with either label invariant, or you can say someone knows like the distribution up to a permutation, then actually you can come up with a classifier that is competitive. So this is what that shows. So I don't know. There's Superman, Superwoman, Catwoman or something. So maybe if you want to be Superwoman, you cannot compete. But when you want to compete with Catwoman, then maybe you can. So it's that kind of thing. You can compete. You cannot compete with some superhumans, but you can still compete with some other superhumans that are still stronger than anyone we know. So that's what it does. So it's a performance of the omniscient label invariant classifier. It's a uniform bound over all k. There's no k in this. And that classifier works in linear time, just like all these estimators. And as far as we know, it's the first uniformly competitive classifier.
Can you explain what that classifier would do in the example, the last example? How does it work?
Which example? So what you need to do is you need to do the good. I described to you how the good Turing estimating will work. So you need to look at that and do this calculation. It's a little tricky, and then you need to also do it over sequences, over pairs of sequences. So it's not easy. It's at least as complicated as the good Turing estimator does.
Okay. But why would it do better in that last example?
So let me ask you another question. So you remember the good Turing estimator that what it did was it looked at empirical frequency essentially, and it looks at the next one. Why would that be better than the empirical frequency? It's the same kind of reason that you actually. So in other words, in order to explain this is a complication on good Turing because you need to estimate two sequences at the same time. In order to understand why this will work better than empirical frequency, it's easier to explain why good Turing will work better than empirical frequency on a single sequence. Do you understand that? Probably no. So one should better explain that, and that will take a little bit of time. So in fact, you guys asked that we give like an open talk. There's an open talk coming up, and it will be about good Turing estimator. So if you can wait till then, I'll try to do my best to explain why good Turing works better than others. But it's not. There are many explanations for good Turing. You can look at them. None of them is like I can tell you in one word. If you want, I can try in like 3 sentences, maybe at the end, just because I can try to tell you. But I'm not going to do much justice to this. But the question is, you have 2 samples, and you see how many times like an element appeared. The question is, should this probability that you assign, should it be monotone in the number of times this element appeared? And the good Turing, they tell you no. You should look at how many times other things have appeared as well. It's very unintuitive, but it's true.
Because Turing, after all.
Yeah, that's right. That's why they make a movie about that and not about empirical frequency. All right. Okay. All right. Okay. So here there's also a low bound. You can prove a low bound, but the bounds are not matching, the upper and low bound. So there's a little bit of gap between them.
So you didn't explain yesterday why Turing was good?
No, I did not. Yeah. What we did explain yesterday was one aspect, but I don't think that's what he's asking about. We showed that good Turing is unbiased. That's the first part of the explanation, but that's not the kind of explanation he's looking for. This explanation is in terms of if you're going to prove things, you need to prove that they're biased.
It would be nice, I agree with Anand, that it would be nice to have a direct explanation on that example, right? Because empirical frequency is so intuitive. And now you're telling people a very shocking result, which says that you can do better. Somehow you should be able to explain it directly in that example why you...
I agree. But what I'm just saying is, in order to explain this example, an easier thing to explain is why the probability that we assign to an element should not be just a function of the number of times this element appears. It should be a function of other things as well. Because if you remember, good Turing assigns to things that appeared 5 times, it assigns what empirical frequency gives to things that appear 6 times. Why should we care?
So in the example before, any estimator that has an error that goes to 0 must assign the small numbers asymptotically to the first class, right? Is that correct?
Correct. Correct.
Because otherwise you can't. So
Correct.
there must be a reason.
And
this thing will see that all the small numbers must be coming from the first.
Right, but asymptotically, notice that asymptotically empirical frequency will also do the same, right? We just chose n was the number of samples, and k was either n or 2n in this example. So it was not in the asymptotic regime, the number of samples is much larger than the alphabet size, it's actually same or smaller than the alphabet size. But yeah, asymptotically, good Turing will converge to empirical frequency. If it didn't, there would have been logical error.
Sure. Is it empirical frequency will not, right? Because even as n grows, the empirical frequency, when you see a small number, with a constant chance, you will always assign it to the big thing.
No,
right?
so the thing is, no, just 1 second. So maybe we're not talking about the same thing. When I say n grows, I'm thinking you're fixing the distribution. You're fixing the distribution and let the number of sample grows. If that's what you're doing, as the number of sample goes to infinity, you'll estimate the distribution correctly.
Do you think have the k and n adjust the way that...
No, exactly the way you were scaling things.
Yeah.
Oh, okay.
You proved, right?
Right, yes, no, okay.
If you prove that
Yeah.
overlap with at least a constant chance, that's how...
Right, yeah, this solves for any n. This holds for any n. I thought you meant asymptotically like with... No. Yeah, correct. Mm-hmm.
So the empirical frequency estimator, that's what you proved, right?
Yeah.
Will assign with at least a constant chance the small numbers to the big distribution, and that's why it's making an error.
Correct. Mm-hmm.
So any estimator that will have a vanishing error will learn as n grows, in your example, to assign all the small numbers to the small distribution.
What it will do is it will look. So in this case, you can learn more because you can see there's more structure to this distribution, right? If you have n samples and you have a distribution over n things, you'll see one kind of distribution, not just by looking at your sample. And if you have n samples over 2, and you'll see a different kind of spread. And this estimator will learn that, even though it does not. You didn't tell it ahead of time that it's over n and 2n samples, but you will learn that there are different things, and it will learn that. So it will take that into account. Right. Okay. So if you want, come to the other talk, and you'll hopefully understand. But you need to understand first why good Turing works better than empirical frequency, and then you can try to look at that. Okay. Okay. So I think at this point you asked so many questions. I should ask you at least 2, and these should be easy for you. So we said that you can approach the best performance like up to 1 over n to the 1/5. And how can we approach it for you remember we had an example of this joint support? So this says maybe that we should be able to approach the best error, which was 0, but we argued that you cannot. Your error will be at least actually 1/4 or something. So how can we, is there contradiction here between this and the first example? So if the 2 examples have this joint support, the best you can do is 0. But that's right, label invariant, so we know that. So in order to get 0 in the other one, you need, like we wrote here, label variant classifier. But if you did the label invariant classifier, then you will not be able to get 0.
Catwoman.
Yeah. And the second thing, these are legacy slides, so this used to be 1 talk. So what is K? Now we need to go back 3 slides, three talks. And remember, that's too much, I think, even for me. So, all right.
But J. Kuma confused us. You weren't here.
That's right. It's sigma, right? It's sigma. Or what's your notation?
He tried to
that's right. I understand. Right. Yeah. Right. Okay. Right. Okay. So I just want to show you an experiment. So I'm sorry. I'm sighing because always time estimation does not work. Okay, so some experiments. I want to adjust our expectations. Okay, so I know David is very excited doing something very unintuitive, or what you call it. So maybe you think that. So show your experiment. Maybe you think that using this, you'll be able to reduce the error from you make an error of 50%, you'll reduce it to 1%. Okay. No, if that was the case, we could take an estimator that has an error of 50% reduced to 1%. I would not be presenting it to you. So, so just recall the Netflix challenge, okay? They asked people to improve on their estimators, and they said, okay, they gave people, I don't know, a certain period of time, and said, if you improve our estimate by 10%, then you stop the game, 10% is sufficient, and give you $1 million, okay? And I don't think it happened. I think it actually continued. So 10% improvement on things that people have been doing for like the last 300 years, 10% is quite a bit of improvement. So don't expect more than 10%. Okay, all right. So, okay, so given that, let's look at ZIF distributions. So looking at two distributions, one is 1 over I, and one is 1 over I to the 1.5. Okay, so this ZIF distribution, common distributions for the distribution of words. Okay, so look at two ZIF distribution. One is linear, and one is 1 over I to the 1.5 is k. J. Kumar's alphabet size is 100. It's pretty modest. I'm not even saying let's look at a trillion. Just look at 100. It's a very small number. If it works here, then it will work for larger numbers too. Okay, so what we're doing is we're going to plot the error versus the trailing length n for empirical frequency and for this proposed classifier. So here they are. So this is the number of samples that you train on, okay? And this is the error probability, okay? And so this is what empirical frequency does, and this is what this estimator does. So if you see, for example, for 50, if you train on 50 samples, then you go down from something like 43% to something like 39%. So you reduce it by 4%, which is 10% of your error, which is the Netflix limit. So, yeah, we gave ourselves $1 million, and
the new limit, not certain limit anymore.
The Netflix limit. Right. So, and so what this is supposed to show that these things are not just like asymptotic, as k is the trillion and n is a billion and so on. This works for small numbers as well. So. So I think, so I have a whole bunch of, I have another 50%. So. Adel seems to be relaxed. I think there's only one person here who seems to understand it. All right, okay, but so maybe I'll stop here. So maybe just briefly tell you, I was going to tell you some other results. So some results that we have is, you asked if we have n and n and 1. But you can ask what if you have n and n. So what kind of results you get there. So if I give you like one email and another email, and then a third email you want to classify. So that's one thing. I was going to talk about closeness. So this is classification. Another problem is closeness testing. Someone gives you two samples, and you ask, do they come from the same distribution or from two different distributions? Like you see two manuscripts, the same person wrote them or two different people wrote them. So this problem turns out to be very close to this problem. I was going to see how they're related. So the same techniques will hold. I was going to talk about estimating Renyi entropy. So that's a very recent work that I mentioned, Himanshu. People have been trying to estimate Shannon entropy for a long time. Some years back, Paninsky showed, so people knew how to estimate linear number of distribution of a size k, how to estimate the entropy with a linear and k number of samples. Then some years back, Paninsky showed that you can actually do it with a number which is sublinear. And then Paul and Greg Valiant showed that you can do it with, if the alphabet size k, with k over log k samples. And then Nihong, who is here, improved this result and showed really what is essentially the best you can get. That's a very recent paper, last few months, I think. So whatever it is, it's, if not k, it's k over log k. And once you get from k to k over log k, then you should ask Hyung what is his constant. And I asked him yesterday, and he was non-committal. Like when you look at k over log k, when you try to estimate, what is the constant in front that you might expect?
No error.
Okay.
So epsilon, if you want to get epsilon beats,
Mm-hmm.
k over log k epsilon squared.
But I'm asking actually, what is the constant in front?
I don't know, it's some huge number.
Some huge number. So you're gaining a factor of log k, and you might be losing a large number. So, but in any case, these are great results. I mean, but still, you need a number that is linear for all reasonable k, a number that, let's say, is linear or close to linear. So the question is, again, in the sense of the art of the durable, maybe instead of Shannon entropy is a measure of randomness. But who says you want to look at the Shannon entropy? You can also look at Renyi entropy. Okay, so Renyi entropy is generalizes Shannon entropy. It has a parameter, and if you look at the value of the parameter as this alpha goes to 1, it's actually the Shannon entropy, but you can look at different ranges of the parameter. And what Himanshu's question was, what if we try to estimate the Renyi entropy? And then you can show that if you try to estimate Renyi entropy of integer orders, then actually you need a lot less than linear. So for example, Renyi entropy of order 2, you need only square root of k samples. So I was just going to mention this result anyways because there's going to be, in March, there's going to be the workshop, and he's going to talk about that. So things like that. And then Ashkan.
It's connected to the collision.
Correct. For k equals to 2, it's related to collision probability. Correct, exactly. And some work that Ashkan has worked on, which is looking at continuous distributions that have few modes, and so like they don't go all over the place, but they have few modes, and how can you deal with those? So the results for all these kinds of things, we don't have time to go over. So yeah, so I think, and while on like advertising, just one last advertisement. I actually made a beautiful slide and got lost when I turned off my laptop because they were in keynote. So in 2 weeks, there's going to be the ITA workshop in San Diego.
Yes, we know that.
And David invites everyone, right, to his hotel room, right? Okay, so it's actually a really good program. We until last year we went like to four parallel sessions. This time we have to go to 6 parallel sessions. There are lots of people from different fields. Computer science, there are over 90 people I counted participating.
90?
Over 90, yeah. Participate. Well, we actually have over 500 presenters. So, and it's in a beautiful place. It's in those are the slides that I was going to show you. It's in one of the most beautiful locations in California, the Scripps Pier and so on, La Jolla, but specific part of La Jolla. And we have some sessions on entrepreneurship, including a play. Did you see? There's the Entrepreneur. It's a new play, and actually Alex is organizing what?
Music video.
Yeah.
ITA Vision, yeah. So it's been posted, right? So.
Right. So if you can, make videos, you can make you can maybe get big prizes that Alex will.
Music video competition.
Right. So if he.
Is it like a Netflix challenge?
Yeah. The worse the video, the better the chances are. So anyways, please try to come, and if we may still have a few slots. So if you want to speak, let people know. And anyway, so if people have more questions, I can answer them. But if not, stop here.
Great. Let's thank Alon. He went through a lot to come to give these talks, so really appreciate it. Lots of cell phones,
yeah, that's
laptop wet, and so forth, and now he lost half the slides. So any questions?
So is the classifier you propose always better than the empirical classifier, or can it be that the empirical?
You can show that it's essentially always almost optimal, but it could be that for some things the empirical will be better, but not by much.
So in other words of asking the same question in a more concrete way, is there a way that I can feed and get the red line above the blue line or the
you might be able to get it above, but not by much. Not by much. Not by much. Yeah. Some of these things still need to be analyzed exactly, but not by much, because we show that it's for every PQ it's almost optimal. That's the essence of the proof, right? So you have from just to be a little serious for a second. So we have this, right? So it's at most n to the 1.5. So this is by how much the other one could be better. No more than that. Okay.
If you continue your picture on the next slide, you have kind of we know that the...
Yeah, so eventually you'll get to the regime that Erdal was asking about. Both of them are going to converge to 0. Actually, not to 0. Both of them in this case, because you have a single one, so you'll not, but they'll converge to the same thing because you learn the distribution. So they'll converge to the summation of the minimum. So as n grows to infinity, if you keep the distribution, and n goes to infinity, you learn the distribution, right? So then once you learn the distribution, you're back to the hypothesis testing, and then it's summation of the minimum of the two probabilities. That's what you do. Because you're doing classifying a single element, like he was asking, not Z is just one element.
So you should be able to make more impressive pictures by
possibly. I'm not sure. Possibly. Yeah, I'd like to see the most impressive. I would like to beat the Netflix. Right. Okay. Yeah.
Okay, so let's take a thanks.
Yeah,
Alon
thank you.
again. So